All right. Well, welcome to class for what is today? Tuesday, April 7th. If you're in the Chico area, it is a lovely day. Blue skies and some overnight rain, and should be a lovely morning. Okay, so course stuff. A couple of things. First of all, as some of you are graduating, and so this is less interesting to you, but those of you that are not graduating, you should make a concerted effort to do some advising with Dr. Ayers prior to registering for classes for the fall. As you can imagine, that is a little bit of a crazy thing. And so you will definitely want to talk to Dr. Ayers about, what courses you should be taking, what courses are going to be offered. As far as we know, that includes all the things we're normally expecting to have offered, but it changes minute to minute. So you should definitely talk to Dr. Ayers before you register. Other course announcements. SETs are now available. I do not care what you do with those SETs. I am going to argue at any point that all of my SETs for this semester are completely and totally garbage.
What's an SET?
Oh, student evaluation of teaching.
Oh.
It's those things you have to do every semester that you say, does my professor suck? I'm telling my students, I'm supposed to encourage you to fill out your SETs. I don't care. You've got 18 things to do. You don't want to do your SETs? Be my guest. I am taking the attitude of that is so low on my priority list right now that I'm amazed that they're even, frankly, it bothers me that they have the gall to ask you to do that at this point in life. Like that wasn't cut with the essential things. But such is life. Okay. So, but SETs are available now, I think, through the end of next week. One other announcement that you might be interested in is that campus is strongly pushing to be open again in the fall. It's not clear what all will be open, but we are not scheduling online classes for the fall. We are scheduling in-person classes. That is a campus-wide encouragement, basically because I think students have figured out and administrators have figured out that students have figured out that online classes are pretty much terrible for the most part. And so, we're scheduling everything on campus. The other piece of news is that we've been told the physical science building, the new one, will not be finished in time for us to move in before the start of fall classes. That means we'll still be in our grand old physical science building next fall. It also means that right now the schedule is a little bit up in the air, which harkens back to my other announcements, that you should definitely talk to Ayers before you try to register for classes, because we're still trying to, we basically had the whole, if you imagine like you build this nice like Lego castle out of the schedule, right? That announcement was basically like your kid brother with a baseball bat, like just smashing that whole lovely Lego structure you built. So Ayers and Claire are desperately trying to build a new schedule for the fall. I am assured they will have something before registration opens because they have to. But you should definitely do the advising with Ayers prior to registration. That will also help him make sure that he's thought through where all the classes that everyone needs to take need to go on the schedule. Because it's entirely possible that we will have to have some overlaps between different physics major upper division courses, which we generally try to avoid. Okay, I think that's it in terms of announcements. Any questions about any of that stuff? All right. Then let's get started talking about statistics. Bjorn, are you going to tell us all about statistics and probability?
Maybe not all about it, but I can tell you about basic probability relations, which is chapter 2 of the statistics and probability book.
All right, we'll settle for that. Go for it.
Okay. Do you want me to like share my screen or something, or just like yak?
If you find it helpful to share your screen, go for it.
Okay. I mean, a lot of this chapter is like introducing a lot of like notation, so it might be helpful, I think.
Go for it.
It says you disabled participant screen
Oh, I
sharing.
did. Sorry, that's the new default. Oh, now let's see. How do I make you? I don't want to do any of these things. Okay, here we go. All right, that now you should be able to share your screen. Maybe.
Yeah. Okay, yeah. Or do you see it? Do you see my screen? Okay. Okay, sorry. Just had to make, I forgot if I left my mic muted or not. But so chapter 2 is about basic probability relations. So it's basically introducing a lot of the logic and axioms that go behind like probability and you know, how do you talk about, you know, if you expect event A to happen, but you don't expect event B to happen, and a lot of the notation behind that. So this section 2.1, it's a lot of it is introducing a lot of the, you know, kind of a lot of like Boolean algebra type stuff that that a lot of us might be familiar with already. So the example this book uses is they talk about an event as, you know, if an object is a sphere, or if an object is a cube, or if an object is red, which kind of seems like a weird thing to call an event, but that's what they use for the example. So for instance, if your object is a sphere, say you know your object is a sphere or a cube, obviously it can't be both. So that would be an exclusive or, where it is either a sphere or either a cube. So they call it event A as you. So they have, it's either event A or if you have a bar above A, that means not A. And then if you know, say that an event is certain, they use an omega. So that would be like, you can think of that as always true. So say you know the object is for sure a sphere or it's a cube, then then that event would be an omega if you're talking about object being sphere or cube. And if it's never going to be a sphere or a cube, then if you're talking about is the event a sphere or cube, that would be a 0. That would be an impossible event. So that's just kind of some of the basics. And then they talk about, they introduce the notation for ands and ors. So an or is kind of this upside down U. Let me zoom in a little bit. And then an and is kind of like the, sorry, the and is the upside down U. And the or is kind of this right side up, this symbol right here. And they have like some of the basic some basic relationships if you have ands and ors. So if, for instance, if you have object A, or if you have event A, if you don't have event A and event B, that's the same thing as you don't have event A individually and you don't have event B individually. So a great mind once said, if you're not having broccoli or you're not having SpaghettiOs for dinner, that's the same thing as you're not having broccoli and you are also not having SpaghettiOs. Or say if you are, you say that I can't have broccoli and SpaghettiOs for dinner, that means I'm not having SpaghettiOs or I am not having broccoli individually. So that's just like, and then, so a lot of this for me was already like familiar from like electronics. And then this one thing was kind of new and unfamiliar to me, which is sort of this sort of sideways U, which is A implies B. So what they mean by that is basically if event A happens, then event B always happens with event A. And so all this they use a little bit later on in this section 2.2 here, where they go and introduce the probability of the probability axioms, which is basically just these are the basic truths about what it means to have a probability. So for instance, a probability always has to be some kind of positive real number. And if your probability equals 1, that means that event is certain to happen. That means that event is definitely true to happen. I think the beginning of this book says, one argument is that it's not the only certain events aren't just taxes and death. You can classify other events as being certain to happen, but taxes and death would be one example of, oh, the probability is 1. And then the last one is basically the probability of, it talks about if events are, I think this is talking about if events are independent, or that might be later. The probability that A or B applies is equal to the sum of the probability that A or that B applies. So basically that probability is commutative. And they introduced some more about some more of sort of probability identities. Does anyone have any questions so far? Okay. So then I think section 2.2.2 sort of introduces like independent events and what's called Bayes' theorem. So one more notation they introduce is a conditional probability of an event. So basically, the example for this is like going back to maybe the example of, like different objects that are like spheres or cubes, or maybe they're red, blue, or green. This is like saying, what is the probability that an object is a cube under the condition that it's also red? So that's what they mean by like a conditional probability. And they also introduce what it means if you have an independent event. And the definition for that is that if the probability that event and A happen is the same as if you were to multiply the probability of A times the probability of B. So I think, oh, and then the last one here is what's called Bayes' theorem. So this is basically, they basically construct this out of just these things that we already know about probability. And they show some applications later on. But just from this chapter alone, it's not completely apparent to me the total extent of this statement. But there's some examples later on of basically how you can use this. So one good example right here actually is for some of the notation is like, you can think of a deck of cards, and for some reason they use like 32 cards instead of 52. But like it's a good example of like the conditional probability, where say the probability of getting a heart, okay, that's 1 in 4. And the probability of getting a king is 1 in 8. And if you were the conditional probability of getting a heart, given that you have a king, that's still going to be 1 in 4 because you have 4 kings and one of them's a heart. And let's see, they show some more. I didn't really. They show some more. Some other examples. They talk about random coincidences. I didn't really understand this one quite as much. Basically, it is showing that if you, I didn't really get this one, honestly. This,
So I'll just chime in on there. That's a particle physics application, because in particle physics you have what's called background events, which are just random fluctuations in your detector, or it's a electron that didn't come from your experiment, that instead came from the fact that there's a little bit of uranium in the metal you used, and so it occasionally decays, or random stuff like that. So they use pairs of detectors, and if both of them go off, then it came from a certain location based on the way you arrange the detectors. It's not really important to understand the example. That's the context for it.
Okay, and then the last two examples are where they apply this, or where they apply Bayes' theorem. So I think this one is actually this was kind of the way I understood like how it works the best, which is just looking at, trying to determine the probability. This is like how you can actually use it to determine something that like might not be like completely obvious, just like if you were to look at it without Bayes' theorem, but it's determining the fraction of a student population that is women, based on just knowing the fraction of students in the total population, the fraction of women in the total population, and the fraction of students in out of all women. If you have just those three things, you can determine the fraction of women among students, because you basically just construct that equation we had earlier right here, and you can extract the probability of women among students, and so they can figure that out 0.45 from the data they have already. And they show one more example, which is basically how you can apply it in a scientific context. And it's another particle physics thing. So yeah, that's about it on that. That's all I got there. Does anyone have questions? All right, well, hopefully that is enough to, then if you see later, the notation for any of this stuff, you know what it is.
Great. Yay. Well done, sir. All right. Okay, so the real point here, as Bjorn was mentioning, is we're kind of getting up to speed on notation. The other thing is thinking about probability is important because essentially what we're going to do, and chapter 1 sort of discusses this, is we're going to want to ask questions like, you know, in my simulation, what fraction of stars end up moving at more than twice the initial velocity or twice the escape velocity from their galaxy? Or, you know, what fraction of trajectories are achievable at less than a certain amount of delta V? Or, right, all of these types of questions. These are the statistical sort of data analysis questions, because even though we're not using like observed data, we're generating our own data using a model, we are still able to ask statistical questions. And it turns out that those are some of the most useful ways to analyze large data sets, is to go after them statistically. So I wanted to play around with this just a little bit to hopefully sort of make things a little more concrete. So what I want to do here is I want to build the probability of how many spaces you're going to move in Monopoly. Okay. So has everyone played Monopoly? Let me ask it this way. Has anyone not played Monopoly? Okay, so somebody give me the rules. What are the rules for how you move around a Monopoly board?
You roll 2 dice and you move that many spaces.
Unless,
And
You go to jail.
well, okay, we're going to ignore going to jail and the cards that make you move. But what happens, there's an unless there, right?
Reach go.
Well, you reach, then you just keep going.
Oh, okay.
Doubles.
It's been a long time.
What happens? If you roll doubles, you get to roll again, right?
mm-hmm.
And you get to do that up to 3 times. So you can roll, if you roll doubles, you get to roll again. If you roll doubles again, you get to roll again, right? That third set of doubles sends you to jail, which we won't worry about here. But basically, so this is an interesting question. On average, how far does a player move in a Monopoly game with each roll, right? What's the distribution of possibilities? So if we were to try to figure this out from an analytics standpoint, this would be quite hard, right? Because we have to figure out, first of all, what are the odds of getting doubles? And then we have to figure out how that new thing changes. But here's the cool thing about using computers. We don't actually have to do it analytically. We can do this, we can just simulate it and look at the distribution. Okay, so let me share my screen here. Okay, is that big enough that you can see it fairly well? Anybody want it larger?
Maybe just a bit.
All right, we can do a bit. How's that?
That's good.
Okay, so we've got 2 dice, and we're gonna roll. We're just gonna start rolling 100 times, but we could easily crank this up. Even my poor little laptop can handle a lot of dice rolls. And the dice rolls are here, where I do a random integer between 1 and 6 inclusive, and I have to tell it how many I want, so I need the number of dice by the number of rolls. And what this will make is a nice 2D array that gives me, if I roll 2 dice 100 times, it'll give me the values of those dice, right? Now, if I just wanted to ask what's the distribution of numbers I would get from just rolling 2 dice, all I need to do then is add up the dice rolls along axis 0, which is the number of dice, right? So you're just going to add up the first die you rolled plus the second die you rolled, okay? And then I'm going to create this, what I call the roll underscore bins. which is just the bins for a histogram that contain all the possible numbers, right? So the minimum I rolled to the maximum I rolled, and I actually have to go to +2. And the reason for that is a little obscure, but it's because A range goes up to, but not including the largest number. So that's why I need +1. And it turns out that the way the histogram function works in matplotlib, it actually wants the edges of the bins, right? So it's doing so it does a bin at 0, a bin at 1, a bin at 2, a bin at 3, and and so you need a bin that is off the end of your distribution. Otherwise, it doesn't put things. It has a hard time with 6s, basically, if you're thinking about it just in one die. So if I roll this thing and I pop up a window, this is what I get. I get a histogram that shows me the distribution of rolls, right, for 100 dice. And you'll notice that I got 26 7s, which is not surprising. If you've ever rolled 2 dice, you know that you get a lot of 7s, right? And if I rerun this thing, I'll get a slightly different distribution. But if I roll it many times, I'll see that it averages out. So instead of just clicking that number, I'm going to roll 10,000 dice, and I'll see that I get a nice distribution, and it's not going to change very much. If I do it again, I get basically the same shape every time. Basically the same shape every time. Not exactly. It'll vary a little bit. But the more dice I roll, the more likely I am to cut down on what's called random error, or the idea that when you roll 2 dice once, you can get a lot of different things. But if you want to roll them a lot of times, the probability starts to win, right? You could call this the casino effect. This is the, if you go to the casino and you play one hand of, or you do the slot machine one time, hey, you might win, you might lose. But over a long time, the casino is going to win, right? The casino knows the distribution, and on average, they're saying that we know the distribution, it's going to be this. We're going to figure out how to make it so that we, on average, win over the long term. Okay, is that clear what I'm doing here? Does this make sense? Okay, so this thing that I'm generating is called a probability distribution function. What that means is, if you give me a number, like the number 5, the probability distribution function tells you the probability that you would roll a 5. Okay, so it's a function that gives you probability. And we can actually make this thing give us probability instead of just the number of outcomes. If we come over here to the histogram and we do density equals true. It turns out the density equals true normalizes this histogram. And so now it's going to report probabilities, right? For any one roll of the dice, the probability that I'll get a 7 is about 20%, okay? Whereas the probability I'll get a 6 or an 8 is about 15, 16%, okay? And so on down you go. Okay, so that's the probability that we're going to get, that we would do if there were no doubles in Monopoly, right? So now let's add the doubles. So what I'm going to do here is I'm going to change this slightly. I'm going to make dice rolls an empty array that is n dice plus, because we can have additionally up to 2 more rolls, right? If we roll doubles, we get to roll again. If we roll doubles again, we get to roll again. So I'm going to add on 2 extra rolls, okay? And I'm going to make it n rolls, okay? And I'm going to make it so that I feed those random numbers that I generated into the first two rows of that array, right? And if I run this thing, I should find that it gives me exactly the same result as it did before, because if I open up my dice rolls, right, I'm not sure you can see that. I can't make that one bigger, unfortunately. But I don't know if you can see it, but the 0th roll, right? I rolled a 2 and a 4, and then I had zeros here. So they didn't add anything, right? When I added up my dice rolls for the dice sums, it didn't add anything. Okay, so now we need to add some code here that handles doubles. How do we do that?
If dice rolls at 0 equals dice rolls at 1, then you add another counter.
Okay, so we could do this. We need to do that for every point, right?
Mm-hmm.
So there are two ways we could do this. We could do this with a for loop, or we could do this with a where statement. Which do you guys want to do?
Let's do the where.
Okay.
What's a where statement?
What's that?
What's a where statement?
Ah, then we're definitely doing it with the where. Okay, so I'm going to make something I call doubles locks. There's locations of the doubles, right? And I'm going to do it with the where function, which is in NumPy. The where function takes a condition. So my condition here is where dice rolls, the first roll, right? So 0, comma, everything equals, whoa, I hit the wrong key there, equals dice rolls 1, comma, everything. So what this is going to do is it's going to create an array that contains the indices, the locations within the array where the first roll equals the second roll. So let's turn this back down. Instead of doing 100, or instead of doing 10,000, let's do 20 of them, okay? And there's my distribution, but that's not really what I'm interested in at the moment. What you'll notice here is that if I look at my dice rolls, there's one set of doubles there, there's another set of doubles there, there's another set right here. Any more? Nope, that's all of them. So I rolled doubles 3 times, okay? So I should have, in my doubles locks, I should have an array that says 0, 2, and 7. So let's see if that's true. So first of all, doubles locks is a tuple of arrays. Don't worry about that too much. But if you look at what's in it, oh, what did I do? Oh, I see. Let me try that again. You'll see it is an array that has 0, 2, and 7 in it. So now I know how many doubles I need, right? So now what I'm going to do, oh, wait, I'm sorry. This should be 4 because I'm going to need to roll dice. I'm going to roll 2 dice 2 more times. Okay. Sorry, I just realized I had missed that. Okay, so now I know where the doubles are. So I don't have to re-roll everything. I can just re-roll those, right? I can say that dice rolls, or let's call it this way. Let's call it double rolls is going to be some new random numbers. So I'm going to do the same thing anyway. This is rand int. I want it to go from 1 to 6, and I want it to be of size. Okay, let's make something to help me out here. I'm going to make something called n doubles, which is equal to the length of. Now, here's the thing I have to be careful of. Where returns a tuple of arrays? It's kind of a complicated thing, but we only want the array. We don't want the tuple. So what I'm going to do is the length of double locks and only the 0th element. That means go into the tuple, grab the 0th element, which itself is an array. Okay. So that'll give me the number of doubles, and my size is going to be equal to 2 and n doubles. Okay. So now those will be my rerolls. Okay. And then what I'm going to do is I'm going to do something clever. I'm going to write this as dice rolls sub. I only want the ones where I had doubles, right? So I'm going to go double locks sub 0. That's an array that contains the locations where there were doubles. I want to put this into the I want to put it into the 0th row and the first row. Okay, I'm sorry. I don't want to put it into 0 and first. I want to put it into the second and third row is going to be equal to my new rolls. Okay. Now let's see what that does. Now, of course, it'll generate new values. So we'll have to, what did I do wrong here? I've got a shape issue.
You got your
Oh, I
axes.
know. I need to reverse these two. Yeah, okay. The way I set up my oh no. That's not what I need to reverse.
Yeah, line 23.
23 is the one I need to reverse. I need to put this here. There we go. Okay, so let's try that again. And I get stuff. And you'll notice that I got some doubles, right? I have a probability, it's small, but I have a probability of getting a 12 and a 16 and a 17 and even an 18, right? And if we look at our dice sums, we'll see that. There, I must have had a double because I got all the way out to 17. I must have had a double because I got all the way out to 16. I must have had a double because I got to 18. And this one actually is just a 12. So I could have had a double for some of these, right? And we can actually look at that if we look in our dice rolls, right? There we go. On roll number 4, I got doubles, and so I rolled again. On roll number 10, I got doubles, so I rolled again. Actually, here's an interesting one. On roll 12, I got doubles, and so I rolled again. But the total only came out to 5. So it impacted the probability that I'd move 5 spaces. So anyway, we can, and so now if we crank this up, right? If we do 10,000 rolls again, we'll start to see something interesting happen. Okay. What you should notice here is that there's a big spike in probability in the middle of this distribution. Why? Why would we get a spike in probability down here at, like, let's see, this one's 5, 6, and 7?
Because that's still the most likely that you are to roll. Because
right. But why? But
you're more likely than not to not roll doubles.
So let me crank this up even one more. Let me do 1,000,000. Actually, that's 100,000. And we'll see these things. We'll see these probabilities. Okay. By the time we get to 100,000, what we've really got here is a pretty good estimate, right? And so what you'll see is that what Monopoly has done by making these rules is, first of all, they've made it so you never only get 2, right? Because if you roll snake eyes, you roll a 2, that's doubles, so you get to roll again. Okay? So the minimum you could possibly move is 3. And then what they've done is they've made it so that these are all roughly equal probability. 6, 7, and 8, right? Oh, I'm sorry, this is 3, 4. So this is 5, 6, 7, and there's 8, 9, and then you get here to 10, right? And it's possible to get all the way out to 21 or 20, I think, actually. Okay, so we're feeling good. Let's do it again. Let's turn this down because we're gonna have to play with it a little bit. Okay. Now we're gonna do one more of these, right? We're basically gonna take this whole thing and we're gonna repeat it, but instead, so we'll call this double lock 2 is where 2 equals 3. And then n doubles 2 is where is the number of doubles for that. We're going to re-roll them. So double roll 2, n doubles 2, dice rolls 2, or dice rolls, and I'm going to go between 4 and 6. Or I could just do that, right? Because that will automatically go up to the end is my double rolls 2. Oh, and I need a 2 here. Okay, now I've added the possibility of getting that second set of doubles. So if I rerun the thing, I get a distribution where one of the numbers is way out at 25. Actually, there's 2 numbers out there, one at 24 and one at 25. Okay. And if I now crank this back up and do 100,000 rolls, we're going to see our distribution. It is technically possible to move all the way out here past 30 spaces, but it is incredibly unlikely. And we've got this cool like tower thing going on here, right? It turns out, if I zoom in here, the most likely thing to do is to get an 11. A 12 is slightly less likely, and a 13 is slightly more. Okay, so you start getting these weird effects here. And so what we've done is we've numerically simulated our results. We didn't actually go through and figure out what's the probability and what's the probability and the union of the probabilities and blah, 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 blah. What we did is we just said, okay, we've got a big computer. I can roll dice 1,000,000 times in 10, milliseconds. Let's just see what it does. Let's actually try it. And what we find is that's the distribution. That's how far you're likely to go on one roll of the dice. Okay, so now let me ask one more question. What's the most likely versus what's the average number of spaces? Okay, those are different questions. One of them is asking you, where is the peak in the probability distribution? And the other one is asking you, where is the mean or the center of the probability distribution? Okay, and these are all different things. The peak and the center, the weighted center, right, are different things. The peak is simply the maximum, right? So in this case, the most likely outcome, it turns out, if we zoom in, we keep zooming, right? We'll notice the most likely outcome is it's slightly more likely to get a 13 than it is to move 11 spaces, slightly more, but it's there, right? We could do more of these and figure out what the uncertainty on that statement is, but it turns out it's robust. It holds up. Okay, so now here's the question. I want to know on average, how far do you go? How do you answer that question? That's my distribution of probabilities. On average, each time a Monopoly player takes a turn, how many spaces do they move? So give me some ideas. What do you got?
Just take the sum of all the rolls and divide by the number of rolls.
Okay, so you say we just add up all the rolls and divide by the number of rolls.
Or add up all the spaces moved and divide.
So we would do something like we would do something like the, okay, so let's call it average move is going to be the sum of all of the rolls, right? All the dice sums divided by n, what did I call that? N rolls. All right, and if I do that, I get that my average move is 12.24. Let's plot that on our distribution. I want a vertical line at average move. Okay. Oh, I have to give it a Y min and a Y max. Okay. Oh, I see what I have to do. Okay, so I want that to be 0 and
0.2.
well, we'll do 0.2. We'll just ballpark it. Okay, so there's our average roll, right? And we can crank that down a little bit. It's messing up our. Okay, does that seem right to you?
So for the chains, when we have like 3 doubles rolled, that's considered one roll, right?
That's considered one roll, one move, right? Or one turn. I'm using the word roll, but it's not actually the best terminology, right? Because when you roll doubles, you get an extra set of rolls, but it's still the same turn.
Yeah, so then our total rolls wouldn't be the n rolls, right?
So what I'm asking is, how far do you move on an average turn?
Yeah, so if we roll a couple doubles in this data set, then our total number of rolls wouldn't be that n rolls to begin with, right?
I see what you're saying. When I divide it by n rolls, I don't want to know what the average thing I rolled was. I want to know how far I moved per turn. So my n rolls shouldn't really be rolls, it should be turns, right?
Okay.
That when I say n rolls, because you're right, I re-roll when I roll doubles. But I'm not actually asking what your average is per roll. I'm asking what your average movement is per turn.
Okay.
Does that make sense?
Yeah, I think so.
I think I just used calling it rolls was a bad choice, which actually, let me be a good programmer. When you realize that, what you should go in here and do is realize I need to change all those, right? So I'm going to do, where's my find and replace? It's in search. Replace text. So I'm going to replace n rolls with n turns. And I'm just going to replace it everywhere. Okay. So I'll go back through and hey, it didn't change anything. Okay, does that look like the center of the distribution?
I just learned that was a function. I've spent a lot of time.
Oh, the find and replace?
Mm-hmm.
That's a good one.
I would expect the mean to be like shifted to the right slightly more because of all like the
Because
you
of
know
scale.
the small chance of getting the really large number of spaces.
Yeah. So why isn't it? All right, so there's part of this is a visual problem. Part of this is that the way our histogram is plotting. So if we let's zoom in down here so we can see this really well, right? The lowest possible number that we got ever was 5, right? because it's not possible to ever only roll a 3, right? Because if you roll, oh wait, you should be able to roll a 3. Why didn't we ever roll a 3? Oh, I bet we did. I bet it's way down here. No, it's not. We never rolled a 3.
Hold on, go to dice. Go to your dice rolls array.
Dice sums. Minimum is 5.
Go to dice rolls.
Something's weird there. The maximum is 6. Is 5.
Oh, Dr. Nelson. All the times where you didn't roll.
Aha! The zeros.
I knew that looked weird.
The zeros. Good catch. Okay, how do we fix it?
I think in that
Oh,
np.where you can just put that in parentheses and then put an and then if the
0.
dice rolls at location 2 and 3 equals 0, and then you can just put a not in front of that. Would probably work.
That would work. You're absolutely right. You could do it with an and. You could also do this, and this is going to be more computationally efficient, and you'll see why here in just a sec. Instead of checking all the locations, I only need to check the ones that had doubles the first time. So I could just say, I want to only check on double locks, sub-0, right? So I'm only checking the ones that were already had their doubles, okay? Now, I do need to be careful here. Let me show you what this does. If I run this like this, it's going to give me something a little weird, and I'll show it to you here in just a sec. But let me show you what it did if I go into my my dice rolls, okay? It had some issues, right? Like, look at this guy. I rolled a 3 and a 1, and then for some reason, it came in here and gave me that, right?
Mm-hmm.
This one seems to have worked. This one, I don't know what's going on there, right? So there seems to be something wrong here. Here's what the problem is. What this where returns is the indices of this truncated array, right? So the thing that we're feeding into the where isn't a 2 by n turns array. It's a 2 by n doubles array. And then we're feeding that back into n doubles 2. So here's the fix to this. Instead of, okay, I do the where, I look at the length, and then I'm coming down here. And okay, here's what I have to do. This is kind of fun. I want this to go into double locks, sub double locks 2. Yep, one more. Okay, what did I do? Somebody make sense of that nonsense.
So double locks 2 is the array of arrays, or the tuple of arrays. And so you took the integers from that and used the double. So pretty much you're saying double locks wherever we found the doubles of the double locks.
Yes, that's right. So what we're saying here is that what I've done is I've taken the locations of the doubles, and I'm only using those locations inside that had doubles again. Okay, so let's see if this works. Now, if I run this thing, oh wait, it didn't like that. Why didn't you like that? Only integer scalar arrays. Well, of course. What did I do? Okay, so here's my sanity check. Let's see what this is. Let's not do 1,000 or 1,000,000 of them. Let's go back to like 1,000, even 100. And let's print this thing. Okay. And it's still going to barf at me, but hopefully, oh, come on. You're not even going to let me run the thing? All right, fine.
So that might be the sanity check? Wait, because it's giving you that error.
Oh, it doesn't like that in here.
So
Oh, I know. Oh, wait. I have to do that. I have to do that nonsense because double locks is a tuple. Let's make sure that works. Yep, that works. Okay. So if we come back here now, this gets at that annoying thing about where that it always gives you a tuple. There's probably a reason for that. It's always bothered me. It's never convenient for me. So the 0 first gets you into the tuple. So now you're accessing the array, which is what we wanted to be accessing the whole time. And now if we run the thing, okay, there's our 100 times. Now let's do it 100,000 times. And I'm still printing the thing. And there we go. Now we've got weird stuff. So let's make sure our thing works the way we think. Our dice sums go between 3 and 30. Let's see if that makes sense. So the best you could do is roll roll doubles, right? Because I don't have the go to jail thing set on. So technically you should be able to get up to 36.
check the dice rolls.
Oh, their max is 5. Why is their max 5? I told it 6. Oh, maybe I messed it up. Maybe I have to give it 7. Let's try that again. Okay, now my dice rolls go between 0 and 6, which is what I would expect. Okay. So my minimum is 6, my maximum is 36. That makes sense, right? 3 6s. 3 6s is not very common. If I come over here and I look at my distribution, I see a nice set of probabilities. And this makes sense that this peak is slightly shifted over from the maximum of the distribution because that tail is moving out here. Interestingly, you also see this fun alternating thing, right? Where the odd number is more probable than the even number. Why would that be? Right?
Because
Odd's
the
low,
even
even's
number
high.
might be a double, and
What's
the
that?
odd, the even might be a double, and the odd is never going to be a double, or mostly. I mean,
No, you're
on a
that's-
particular roll of 2 dice, I don't think. I mean, it won't ever be a double.
So out here on this part of the curve, right? These are the ones that you have to have rolled doubles to get. So your double is an even number, right? If you get another set of doubles, there's a chance that that has to be an even number, and that'll bump you out to here, right? Way out on the end of the distribution. So what you're seeing here are the ones you lose from the fact that you have this tail of the distribution out here, right? Because the evens got reduced slightly because they could have been, if there's a chance that if you got an even, it was a double. And so you got bumped out here. Anyway, so this is a long and complex way of saying what we've done is we've calculated the probability of rolling any number of moves for Monopoly. Okay? Analytically, this would be a nightmare. It's possible, but it would be a nightmare. Computationally, we just did it, right? All we had to do was figure out how to simulate all the rolls, which, by the way, we could have also done with for loops. and just, you know, gone to town, done 1 million of them or 100,000 of them and seen what the distribution was. Okay, this went on longer than I thought it was going to, but as you can tell, I'm enjoying myself. So I don't feel bad in the slightest. I'm gonna let's stop for questions, and then we'll shut it down for today. And then I think one of the groups was supposed to talk to me at 10, right? No?
Stellar, or sorry, Galaxy, we're at Thursday.
Thursday at 10. Okay, Thursday at 10. That's right. I got confused. And then okay, so Galaxy is Thursday at 10. Let me check. Let's stop sharing this thing. Well, okay, so let me stop for questions. Questions. Comments, concerns.
It makes me want to play Monopoly now.
Okay, so I've got the traveling salesman group at 3 today. Is that right, traveling salesman people?
Yeah.
Okay. And the Canopy Waves group is at 2, right? Did we decide on that?
Yeah, I mean, I'll be there. I'll get Harmon to be there too.
All right. Good luck. I'll make sure Eric knows, but I doubt he'll join the Zoom thing. He can actually join by phone, but I haven't gotten him to do that yet. So.
Does he have a smartphone? I don't think he has a smartphone.
Oh no, not even on. I don't even mean on a smartphone. By telephone.
Oh.
You
okay.
could join these things from a rotary phone if you wanted to.
Oh, is that what all those numbers are for? And when you send
Yes.
those, I see.
Although you just clued me in as to why nobody ever does that. It's because when you say you can join by phone, everybody assumes they mean smartphone. Okay, so I'll let Eric know, and he might be able to join us as well, and then we can talk about the Canopy Waves at 2 and the traveling salesman at 3, and then we'll talk about the Galaxy modeling group at 10 o'clock on Thursday. Sound good?
Sounds good to me.
Okay, last item of business. We need to talk about who's talking next time. So for next time, I would like to go over section 3.1 in the what's these guys' names? The Bohm and Zek book, which Zek is a great name. Okay, who wants 3.1?
It's on
I'll take it.
probability distributions if you're, for
I'll
those who
take
are not aware.
I can do it.
Okay, Josh, you're up. Thursday, 3.1. Okay, so we'll stop there then. Yeah, have a lovely day.
Hey, Dr.
Dr.
Nelson,
Nelson.
I was just gonna ask if you could post the code.